Okay, hi, hello. We're back, I guess. Hopefully this video isn't too long. Um, we have a single goal. Okay, so in the 2 days ago, Vault Chat did its first end-to-end reproduction, and we are going to drill in on it. We're going to see, it claims it was a faithful reproduction. I can already tell that it only focused on like one benchmark from the table. Um, And so like I'm gonna drill in where you're gonna see my back and forth. I'm purposely, you know, I sort of want to like leverage the uniqueness of the app. You know what I mean? Like I built it for to do some cool things, you know what I mean? So like but I actually haven't gotten to express or like actually use all the cool capabilities in Vault Chat. So today, hopefully, I can have a sort of a unique thing where I'm going to be reading docs. In theory, voice mode is able to see the actual markdown file or whatever document I have open, and I can sort of like talk to the voice back and forth about what I'm reading, and then it can like write and take notes in like a second pane. Hopefully, you'll see what I'm saying. Um, in short, yeah, I ran a mission to faithfully reproduce the coconut paper from Meta. It ran, claimed success. I barely reviewed it. The only thing I saw is that close to faithful, um, much better than the previous run. This is the second attempt. The first attempt completely failed. It had a precision issue. It used like floating point 8 or 16 instead of 32. You know what I mean? It was just low. It wasn't a low enough precision, or it was too low precision. Yeah. Um. So after that, what's it called? It fixed it, and then like actually followed the config from the how do I say from the paper. It's like it's public. You know what I mean? So I also did a lot of work on Volchat's harness, because it was too inconsistent. You know what I mean? It's like after that first experiment, it went. I don't. I sort of lost trust in it in a way. So I've been doing a lot of rigorous testing on Volchat's ability to run missions end to end. And we're close. We're really close. So hopefully we'll be able to do another experiment. I would really like to start another experiment this week. But the focus of this video is the coconut reproduction and actually looking into it. It's definitely decently over my head. But that's what we're here for. We're just going to be honest about it. We're not going to be afraid about trying to do. We are going to try to we're going to take big bites and we're going to see if we can chew it. You know what I mean? So let's start by looking for the mission. So like, for example, like I did two interesting things. It's like, cadence fast. I'm completely on a tangent already. Cadence fast is, the agent, the supervisor for the mission is supposed to check in with itself 50 times, and each interval should have been like 2 minutes. You know what I mean? And like, is the harness and configuration to run a mission stable enough that I can do that to completion? It wasn't before, but it is now. And then the second one is for it to check in with itself 3 times with a cadence of 6 hours. You know what I mean? So in theory, you'd run all the way for 18 hours, and like it only checks in 3 times. So like I'm going to be shipping updates. The boxes are going to go down. A whole bunch of stuff is going to happen. Can it still make sure the mission gets done appropriately? And then the hard proxy is I've done a few proxies. It's like the proxies are supposed to be like without spending compute, or spending money on compute. Can you do a similar run to an actual end-to-end paper reproduction, and can you do it successfully? So I've done a few. The first one failed. Second one failed. Third one kind of worked. The fourth one, so close to working, but like there's a bias because I spoke to it and then it noticed something when I spoke to it and it corrected itself. But like that's not fair because like I didn't want, you know what I mean? I've injected into it, you know what I mean? I would have preferred, I want to know what happens if I didn't speak to it, you know what I mean? Because ideally I'm the manager of a lab, you know what I mean? Ideally, yeah, because I want to do two things at the same time. You know what I mean? I want to become a better engineer, but I also just, I don't know. I want to live in the future. I want to make a bet on the future. So I'm going to be the lead of this lab. Okay, so let's see. It was, and the coconut, yeah, the reproduction took, it's whatever. It took a few runs. So they're actually, I had to do like a second mission because the first mission didn't complete. Again, there's like amounts of like control that these things like require. Um, yeah, so it did, we're not done yet. But we do the code finished, just not the mission completely. So let's see, faithful reproduction, and let's see. So what should I read to fully understand this mission end to end? Oops. Oops. Okay. So this is my first time doing this. I don't, what's it called? I only interact with missions on my phone. I'm hoping this works. You know, it should. Claude has done a lot of work. Claude is just insane. You know what I mean? The fact Claude built the whole thing, bro, that's crazy. Um, I think Claude, actually, I'm pretty sure it's GPT 5.5 are technically the workers, but that's fine. That's whatever. Holy guacamole, bro. That's not normal. Okay, so let's see. Here's the end-to-end reading path for this mission in order. All paths. This mission's own spec. Okay, docs. Interesting. Why the last one failed? I'm not worried about that. The paper, I'm not worried about that. The config, I'm not worried about that. The guardrails, you must launch through non-negotiable. I just read. It's clear. Thanks, bud. Um, repro gates, the only launch paths. Verification of the gates work. Okay, so interesting. So I'll read the guardrails. I don't think I like these selections. So I'll read oops, and the docs. I just want to know how. I just want to know what and how you did it. Good choice. Okay. Hopefully this doesn't take you long. Um, then we're gonna do is the split plane. Hopefully that's cool. I'm really hoping that would be sweet. Is so what I'm gonna do is one one chat or not one chat, one screen, one pane is going to be the actual docs that it produced while I was doing the mission, and then the second one is going to be sort of notes. But in both cases, I'm going to like sort of like read the docs, but have voice mode on, and then I'll talk to voice mode whenever I have a question about what I'm reading, or just to talk because like reading sucks. And then I can also have voice mode like write a note of like whatever I think was important. Um, Again, we're taking a risk of like cognitively, it's important to what's it called to actually read, to actually enunciate, and to actually write things down. Um, well, we shouldn't let. Again, I'm choosing to not let the fear of that stop me because I'm still going to take care of those things in other aspects. You know what I mean? I will be hand typing leak code and deep ML problems, and I will be writing from scratch. We will take care of these things. Um, real, read all 4K files. Why am I reading code? I want the story. Oy vey. I think I might give up on this and I might just choose. I'll accept that the gates is probably something I want to see because I'm curious about what it means when it's saying that. And then the stuff in the docs. We'll just go into that. And hopefully this video is a lot higher quality. I noticed let's see, the story, not the code. Okay, but what? Oh my goodness. It's not doing good. Um, what was I talking about? Oh no. It's so over. It's so over. That is a horrible response. Okay. So I'm just gonna go for the harness. I don't know why it's talking about the bitnet. Bitnet is so old news. Let's see. Coconut? Oh, what was the path? Let's see. Where? Repro gates. Landed readme. Okay, let's just do the readme. At least. Let's see. View. Reproduction guardrails for any paper, not just coconut. Fantastic. Room for both. Verifying. Let's just start talking. Okay. I have the README for the reproduction gates. Can you explain it to me in one sentence, please? And thank you.
The reproduction gates are two deterministic checks that ensure a faithful reproduction of a paper's results and prevent silent failures during autonomous training runs.
Holy cow. So I mute myself, and you heard none of that. So this video, brutal. Okay, we don't have a smooth video. It's going up anyway. So basically, I have my headphones in, but in the wrong port. You know what I mean? In like a dead port in my computer that doesn't work. So um, both David is listening to me talk right now. David, please do not reply. And I'm trying to explain to you, how do I say? How do I even mute for David? Keyboard? Okay. Now
I
David's not.
understand you're having some audio issues.
Okay. Holy cow. Um, what's it called? So I'm gonna plug my headphones in and hopefully, you know, hopefully the video isn't very bad at the start or very bad towards the end. Sorry for the awkward part in the video. We'll get better at this over time, hopefully. Okay. David, you don't need to. And and okay. Hi, friend.
Hello.
Okay, can we talk about can you explain what's in this document for me?
This document describes two reproduction gates, the faithfulness gate and the progress gate. These gates are designed to prevent training runs from silently drifting from a paper's reported results or failing without immediate detection.
And how do they work? How are they used?
The faithfulness gate, faithfulcheck.py, prevents training from launching if your configuration deviates from the paper's specified values, especially regarding effective batch size. If it blocks a launch, you must either revert the change or explicitly approve the deviation with a reason. The progress gate, plateaucheck.pym, monitors a running training job and halts it early if it's failing. This means if the run is past a checkpoint epoch, not meeting its target, and has plateaued, it will terminate the box and escalate. It won't stop a run that is still improving or in a warm-up phase.
Okay. And how do they work? Are they just constantly on scripts that they sort of like monitor the missions or they monitor the runs? These run on the box that the actual training is being run on?
The faithfulness gate runs as a pre-launch check, preventing training from starting if the configuration deviates from the paper. The progress gate acts as a runtime monitor, watching the training logs and halting the run if it detects a plateaued failure. While the
And
faithfulness gate runs before the training begins,
hold on.
the
Um, is so in our actual use case, is the supervisor of the mission choosing to run these scripts, or is there a strict cadence at which the plateau check is run? Like, you know, does the supervisor of the mission have to choose to use these?
These gates are integrated into the workflow as guardrails for any reproduction mission, rather than being optional scripts that a supervisor chooses to run. The faithfulness gate is a mandatory pre-launch check, and the progress gate is a continuous run watcher that monitors the training process.
Okay, and you built these because of the failed coconut run.
Yes, that is correct. These gates were developed because the Coconut Prosca run drifted into a significant gap and then plateaued without being detected, leading to wasted resources.
Okay. And this run is what's it called? Or these scripts are genuinely generic. They'll work for future reproductions of a significantly different shape, or does the paper have to follow a standard, or are you going to convert the paper's config into the standard and then use these gates?
These reproduction gates are designed to be paper agnostic and genuinely generic. The faithfulness gate uses the paper's declared keys as the source of truth and allows for configurable key names, while the progress gate adapts to any log format using a metric regular expression. This means they can be applied to future reproductions of different shapes without requiring papers to follow a specific standard or converting their configurations.
Okay, that's fantastic news. Thank you. Um, let's see. So let's move on to something else. Let's start talking about the docs for the coconut run. So
All right, what specifically
let's see. Read it slowly. Lost. Generation of the multi-stage. The stage schedule. Okay, let's go over. I would like for you to read this out loud to me, to be honest. Can you just go over this for me? Word for word. Let's start with let's start from the one sentence idea.
A normal chain of thought model reasons by emitting tokens. It writes Natalia sold 48 divided by 2 equals 24 clips as text, then reads its own text back in. Coconut, which stands for continuous concatenated thoughts, instead reasons in latent space. It takes the model's last layer hidden state and feeds it straight back in as the next input embedding, skipping the decode to a token, re-embed the token round trip. The reasoning happens in the continuous vector space of hidden states or continuous thoughts, never collapsing to discrete words. Why this could help? Decoding to a token is a lossy Rmax, a hard projection onto the vocabulary, and the model commits to one path. A continuous thought is a full distribution carrying vector. It can hold a superposition of reasoning paths and stay in a search mode. The paper shows it behaving like breadth-first search on PROS-KA. Why it's hard? There's no token-level supervision on a latent thought, so you can't just teach it directly. Hence the curriculum, which is Section 3.
Wait, so there's no token level. Yeah, wait. I think what's it called? Is the token level supervision? That's sort of what I was. Two things, I guess. Is the token level supervision as in like a guardrail alignment thought pattern issue, or is it an answer for when the beginning of thought and end of thought tokens go?
Token-level supervision in this context means there is no specific token for the model to predict at each latent slot. Unlike a normal chain of thought where the model generates and is supervised on discrete words, Coconut's continuous thoughts are represented by hidden states. Since these are continuous vectors, there isn't a corresponding token label to train against directly. The special tokens like start latent and end latent are just placeholders whose embeddings are overwritten, not tokens that the model is trying to predict.
Yeah, so what's it called? They just mean that it's hard because you can't encourage a particular thought pattern. You can only allow a thought pattern per se, and then you grade the tokens that emitted from that thought pattern, but you have no control over what the thought pattern looks like.
That's a good way to think about it. Since the latent thoughts are continuous vectors and not discrete tokens, there's no direct label to tell the model what a correct continuous thought should be. The model learns to generate useful continuous thoughts indirectly because those thoughts ultimately lead to the correct final answer, which is where the supervision is applied. The curriculum is designed to help the model bridge this gap.
Okay, let's read section 2.
The continuous thought feedback loop is the load-bearing primitive. This is the heart of the method, implemented in coconut.forward and coconut.py. Read this section with the file open. 2.1, Setup, latent slots in the input. The input sequence for a coconut example looks like question tokens, start latent, 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 dot, 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 latent, end latent, remaining chain of thought / answer tokens. The latent tokens are placeholders. 3 special tokens are added to the tokenizer in run.py. Start latent, end latent, and latent. Their embeddings will be overwritten on the fly. The token ID only marks a continuous thought goes here. 2.2, the loop. This is the whole trick. Inputs underscore embeds equals embedding. Input underscore IDs, which are ordinary token embeddings. Find positions of all latent tokens. For pass underscore index and range, max underscore in underscore latents. Run base LM over the range up to the next latent slot. Output underscore hidden underscore states equals true. H equals outputs dot hidden underscore states, bracket -1, which are last layer hidden states. For each latent slot at position token underscore index, inputs underscore embeds, bracket batch, token
Wait a
underscore
minute.
index.
So, how do I say this? So I'm sort of thinking in like the training scenario is they're going to what's it called? Is the training team just decided an arbitrary number of latent slots for presumably I would hope like not just like a fixed number, but they choose an arbitrary number of latent slots before a particular answer, and like maybe internally they decided, based off of how difficult the answer is, they want to require multiple latent steps or something like that. How are the number of latent steps determined? And in theory, so effectively what we're saying is the training pair is going to be question, latent chain, and answer. You know what I mean? It's like question and latent chain are sort of like the inputs, and then answer would be the output.
The number of latent steps is determined by the multi-stage curriculum, not an arbitrary choice per example. As the training progresses through different stages, more natural language reasoning steps are replaced by a fixed number of latent tokens. For instance, at stage K, the first K reasoning steps are removed and replaced by KK times thought latent tokens, where CC thought is typically 2. The training pair consists of the question tokens and the latent slots as input. The model then generates the continuous thoughts in these slots, and the supervision is applied to the remaining text steps and the final answer that follow the latent
Okay,
block.
so interesting is effectively, how do I say? I don't know if I don't know if if it's analogous to diffusion, but like say you only choose one latent and you choose one latent, but that's not too far from normal chain of thought. So it's, I don't know, the the latent embeddings, the latent thought patterns can only deviate so far from normal chain of thought for it to still work. You're just hoping that you're adding the flexibility, but that flexibility is guided by the fact that it's going to be followed by general chain of thought, and you slowly expand that in the different stages. Is that, a way to think about it?
Yes, that's a very insightful way to think about it. The curriculum starts with pure chain of thought, which is fully supervised, and gradually introduces more latent steps. This warm start provides a strong foundation. The model then learns to leverage the flexibility of continuous latent thoughts, which can explore a broader range of reasoning paths than discrete tokens, while still being constrained by the ultimate goal of producing a correct, supervised answer. The gradual expansion through stages helps the model adapt to this new reasoning paradigm without losing coherence.
Okay. Um, so we actually don't have time to go through all of this.
Understood. What would you like to focus